So, hi everybody. Welcome back to the afternoon session of the joint CIS RIKEN AIP workshop on machine learning and artificial intelligence. So this afternoon we start with Masatoshi sensei on music structure analysis. Looking forward to your talk. Thank you.
Thank you very much. Good afternoon. My name is Masatoshi Hamanaka, and I work for RIKEN in Japan. The title of my talk is Music Structure Analysis based on Transformer. First, I'll explain what the time span tree is. The time span tree is derived by Generative Theory of Tonal Music, GTTM in short. The GTTM was proposed by Reardon and Jackendorf in 1983. Here is a melody and its corresponding time span tree. We can obtain an abstracted melody by slicing the tree down the middle and omitting notes that are connected to branches under a given line. If we slice the tree higher up, we can get more abstracted melody. This shows the evolution of GTTM analyzers and applications. The analyzers are shown here above the timeline. Below the timeline are the GTTM applications. We propose this melodic morphing method here. Here is an overview of melodic morphing method. First, we acquire two time span trees, sigma A and sigma B, from two input melodies, A and B. And then we can acquire the common information of sigma A and sigma A meet sigma B by using the meet operator. We can acquire sigma alpha, which is the intermediate of sigma A and sigma A meet sigma B, because the information of sigma A includes sigma A meet sigma B. In the same way, sigma beta is acquired from sigma B and sigma A meet sigma B. Finally, we can acquire sigma alpha join sigma beta, which is an intermediate of sigma A and sigma B, by combining sigma alpha and sigma beta. By using the melody morphing method, we made this melody morphing melody slot machine. We use a dial type interface that enables replacing the part of the melody segment that the virtual performer will play. Variations in melody segment are composed on the basis of melodic morphing method. So switching the melody segment maintains the overall structure of the melody and only changes the ornamentations. Let me show you a video of our melody slot machine. There are 4 problems in automating the morphing and time span tree analysis. The first problem has to do with the order of the abstract notes in partial melody reduction. For example, the reduced path from sigma A to sigma A mid to sigma B can be written by this formula, but the path is not unique. The second problem is that the 2 notes overlapped temporarily that may occur in the join of 2 time span trees. In such cases, it is necessary to manually select one melody from among multiple generative melodies, and it is difficult to completely automate the morphing. The third problem is low number of ground truth dataset. As ground truth data of the time span tree, 300 melodies and their time span trees are published in the GTTM database. However, the number of datasets is extremely small for running deep neural networks. For small amount of running data, overfitting is inevitable, and an appropriate value cannot be output when unknown data are input. Therefore, we propose stepwise reduction that the maximum process of analysis is set as one data set. Then the number of data set is increased. For example, if the deep neural net directly ran the relationship between 4-note melody and its time span tree, the number of the data set is only 1. If we consider the process of reducing one node to one data set, the number of data set will be 3. A time span tree for a melody consisting of 4 nodes can be constructed by estimating 4 to 3 nodes, 3 to 2 nodes, and 2 to 1 node, and combining the result. Implement the stepwise reduction, the priority of branches must be obtained in a total order. However, there's no detailed explanation on the reduction process in the GTTM. For example, this figure, we can see the 5 level of reduction results, but it is not clear how many levels are necessary. Furthermore, the priority order within one level is unknown. As a solution to these problems, we propose a time span tree labeled by duration of time span. We call the longest temporal interval when a given pitch event becomes most salient as a maximum time span for the event. In other words, the maximum time span of a pitch event considers with the temporal duration of the subtree of which the event becomes the head. As a result of time span tree analysis, the priority of each branch of time span tree is determined within a time span tree drawn with the maximum time span used in the time span segmentation carried out as the first step of the analysis of time span reduction. The branch priority is determined in accordance with the following rules. Priorities are assigned to each level from the top of the time span tree drawn with the duration of the time span. At the top level, the main branches take procedures. At the second and subsequent levels, the higher the priority of branch X is, the higher the priority of the branch of X becomes. This figure shows a time span tree drawn with the duration of the time span. The branch priority is determined in order from the top in accordance with the first rule. Then in accordance with the second rule, branch 1 has the highest priority in this time span tree, and branch 2 has the second highest priority. The second level in this tree is the double node level. In accordance with the second rule, the branch from 1 becomes 3, and that from 2 becomes 4. In the same manner, the priority is determined up to the sixth node level. Now, here's the experimental result for automating melodic morphing. After acquiring the time span tree, there was no attributiveness in the prioritization of the branches, partial reduction, and combination of melodies. And therefore, when the reduction ratio was determined, the morphed melody could be deterministically obtained. In the figure, the notes included in melody A are displayed with the stem up, and those included in melody B are displayed with stem down. Here's an experimental result for stepwise time span reduction. Running and evaluation data were created from musical XML and time span XML. Data before and after the reduction were generated by using the time span tree labeled by duration of time span. The notes in the melodies were made into a one character string with the pitch and the duration concatenated. The pitch was represented as 12 types. The duration was represented by multiplying the duration element of musical XML by 4 and then rounded up to an integer. And here's an example of before and after the reduction. The duration after reduction is getting longer. Here's the experiment result too. The sequence to sequence and transformer melodies, which are kinds of deep neural network, were both trained with 7,362 stepwise time span reduction and training data set generated from 270 songs from a GTTM database consisting of 300 pieces, and 849 evaluating data sets were generated from remaining 30 pieces. And this figure shows the accuracies of evaluating the data. We can set the transformer outperformed sequence to sequence in stepwise time span reduction. And here's a conclusion. We propose the introduced of time span tree labeled by the duration of time span to problems that are difficult to automate due to the lack of prioritization of time span trees branches. And experimental result confirmed that melodic morphing and time span analysis based on deep learning can be automated. Thank you very much.
Sure. Thank you very much for the presentation. It's very interesting. I know nothing about melody generation, but the first piece that you showed us, or I think you call it the slot music machine.
Yes.
There was a secondary instrument playing.
Yeah.
And I was wondering how you make sure that there is a synchronization between the secondary instrument and the first instrument, because I understand that the melody that you generated was for the first instrument, essentially the drummer. And how do you make sure that they are both synchronized in such a way that the tone and you know the accord.
Oh. Yeah, we record background melody first, and then the player, marimba player, play with the background melody. That can be.
So when the melody changes, do you also have to change the background sound?
Yeah, background is the same, and
Background is always the same.
always same.
But there could be a complete mismatch.
The structure is almost music structure is almost similar, so the important timing is yeah.
In the first part, I think you completely use rule-based ideas.
Yes.
And in the second phase, you use machine learning transformer-based. I couldn't get the point of where machine learning is used. Could you explain?
Actually, first area is I use the rule-based analyzer, and then we use the probabilistic model like here. After that, we use the deep learning, and yeah, this is just a deep neural network. Recently, we use the transformer and sequence to sequence.
So to make rule to probabilistic things, you need machine learning.
Yes, it's kind of machine learning, I think, but yeah, accuracy is not so good. So we completely changed the method, like the data-driven. Yeah.
Because with the transformer, you seem to have quite good accuracy.
Yes.
So you literally take 90% of the piece of music and predict the last 10%.
Yes.
And you get more than 90% accuracy with the transformers.
Yeah. Yes.
So the accuracy is basically you actually check if you get the correct notes. No?
Mm-hmm.
So the accuracy you evaluate as you have a full piece, let's say of
not
pieces.
Not I have 300 data set, and 260 is for running, and 30 is for testing. Yeah, completely different. But yeah, data set is about classic melody. So so Mozart has many songs. So maybe similar characteristics.
So maybe I follow up. So the accuracy is measured on the transformer generating the same 30 pieces, or I thought it was generating things that
No.
if it's not existing before, how can you measure?
Generated after reduction the right side. We input left side and output right side.
Could you clarify this, please?
So how do you measure the accuracy? How do you know that you're happy with what happens on the right side?
Left side is before the reduction, and right side the one note reduction after reduction.
Go ahead. Go ahead.
I don't know. I'm passionate about this. So if you wanted to generate these for multiple instruments working in an orchestra, it's a bit of follow-up with my previous question. Would you have to put up rules to make sure that those instruments are sort of making sense musically, so that the sound makes sense? Not one playing a completely different song somewhere, and the rest is playing. One is playing hard rock, and then and the rest is playing classical music.
You mean the this melodic morphing method?
So if you morph this for several instruments, imagine a flute and then a harp and then a piano, it's very different. So how do you make sure?
Sound is different. I think.
Would that be possible to extend this for different instruments?
My method is about using the score, so not related to the sound. Yeah, that is different program. Yeah, but yeah, the point is interesting. So we try to sort it.
That's my last one. If that was to be played by a human, there are constraints. I imagine I was a piano player at some point, and then one constraint is really the size of the hand. And this is not really taken into account. Would it be possible to take that into account so that you have jumps that are dynamically feasible for the hands to move from one part of the keyboard to the other part? Or just
that is
and the constraints are not the same if you play piano than if you play the harp.
That is a good point. But this method is only like mathematics, calculating. So difficult to sort of the hand motion. Yeah, but I have another research about the motion of the hand playing the violin. So that is no. No, but the method can generate the finger shape. Yeah. Mainly the left hand. Right hand is also difficult, but most difficult is combination.
And for that, you use only machine learning, or you use some rules to decide on what is feasible for the hand?
Originally, we used the rule base, but it moved to the machine learning. Yeah, that is better on our research. Yeah. Thank you very much.
All right. If there's no other questions, let's thank the speaker again.